गुड इवनिंग बच्चों, आई एम अबुल्लास। आज हम लोग गॉसेस थ्योरम के एप्लीकेशन पे एक दो एप्लीकेशन डेवलप करेंगे और उसको डिस्कस करेंगे कि इसके पहले हम लोगों ने जो गॉसेस थ्योरम के एप्लीकेशन डिस्कस किए थे वो था कि एक इनफाइनाइटली लॉन्ग करंट, ये चार्ज कैरिंग कंडक्टर की वजह से इलेक्ट्रिक फील्ड किसी पर्टिकुलर पॉइंट पे क्या होता है। दूसरा हम लोगों ने डिस्कस किया था कि किसी कंडक्टर को अगर हम चार्ज करते हैं तो वो चार्ज कंडक्टर के सरफेस पे लाई करता है। तीसरा हम लोगों ने किया था कि अगर कोई कंडक्टिंग शीट है उसको चार्ज करते हैं तो कंडक्टिंग शीट के पास इलेक्ट्रिक फील्ड का वैल्यू σ/2 एप्सिलॉन नॉट होता है, और अगर वो कंडक्टिंग है तो σ/2 एप्सिलॉन नॉट, और नॉन कंडक्टिंग है तो σ/एप्सिलॉन नॉट होता है। अब हम लोग एक यूनिफॉर्मली चार्ज स्फीयर की बात करते हैं। तो यूनिफॉर्मली चार्ज स्फीयर की वजह से इलेक्ट्रिक फील्ड का वैल्यू देखते हैं कि क्या होता है। चूँकि ये चार्ज यूनिफॉर्मली है तो यूनिफॉर्मली होने का मतलब इस पूरे के पूरे स्फीयर में चार्ज की डेंसिटी यूनिफॉर्म है, माने हर जगह चार्ज मौजूद है। अगर ये कंडक्टर होता तो कंडक्टर पे चार्ज सरफेस पे चले आते हैं, तो दिस इज़ ऑफ कोर्स नॉट अ कंडक्टर एट ऑल। अब हम लोग इस कंडक्टर की वजह से यहाँ पे से एट अ डिस्टेंस r हम लोग इलेक्ट्रिक फील्ड कैलकुलेट करना चाहते हैं। सो वी विल टेक अ गॉसियन सरफेस, of a sphere of radius r. So Gaussian surface is a sphere of a small radius r, and we apply Gauss's theorem at this Gaussian surface, and this is E dot ds is q by epsilon naught. So यहाँ पे जो इलेक्ट्रिक फील्ड है स्फेरिकल सिमेट्री की वजह से ये इलेक्ट्रिक फील्ड का डायरेक्शन होगा, दिस इज द डायरेक्शन ऑफ इलेक्ट्रिक फील्ड, इट इज radially outward, and the angle between E and of course area vector E dot ds is 0. So this is mod E ds cos 0 and is equal to q by epsilon naught. At each and every point of the sphere, the value of electric field is same as far as magnitude is concerned. So this E is taken out and ds is integrated. So now the total surface is E into 4 pi r square, and this is q by epsilon naught. So now take this r as x, इसको हम लोग x ले लेते हैं, तो दिस इज E and this is 4 pi x square, and the density is 4/3 pi x cube rho, and this is epsilon naught. X is a variable. Now the electric field is 4 pi, so this is x rho by epsilon naught, x rho by epsilon naught. So the electric field is directly proportional to x. If we take a Gaussian surface of a sphere of another radius, say x is r2, then the electric field is as directly proportional to x, so it will increase. So as we move further inside the sphere, the value of electric field increases because the charge enclosed by the surface also increases. So E is directly proportional to x. Now if we take a Gaussian surface at the extreme point of the sphere, this is the last, this is the ultimate, of course, last sphere, and this sphere includes the total charge. This sphere includes the, of course, included the total charge. So the total charge is included in this, of course, Gaussian surface, and is E dot ds is, of course, q by epsilon naught, and it can be written as here E 4 pi r square, and this is 4 by 3 pi r cube rho, 4 by 3 pi r cube rho, and it is 4 pi r square is equal to 4 by 3 pi r cube rho by epsilon naught. 4 pi cancel, so E is rho r by epsilon naught by, of course, 3. Here also there is 3. If now this is the maximum, of course, electric field, this is the maximum electric field, and it can also be written as E into 4 pi r square is equal to q by epsilon naught, where q is the total charge enclosed in the sphere, and the value of electric field is q 4 pi epsilon naught r square, and this is E max. This is E max. Now if we take a Gaussian surface, this is the sphere which encloses the total charge, but now our Gaussian surface is outside this sphere. The charge is enclosed only by this sphere of radius r, but our Gaussian surface is a radius of larger sphere. Here x is greater than r, here x is less than r. So now E dot ds is q by epsilon naught. The charge enclosed is the maximum. Charge enclosed is not going to be increased, it is the maximum, but the surface area increases, and it is equal to E 4 pi x square q by epsilon naught. So the value of electric field is q 4 pi epsilon naught x square. So if we draw the graph between electric field and distance, the nature of graph will be like that. As we move from center to a sphere, the charge enclosed increases, and that is why the electric field is directly proportional to x, and electric field will have maximum value at the surface when x is r, and after that it is inversely proportional to x. Here it is inversely proportional to x square, and here it is directly proportional to x. So this is the electric field due to a uniformly charged sphere. Of course, the sphere is a non-conducting sphere. Now we will calculate the value of electric field due to a conductor of any shape. electric field near a conductor of any shape now this is a conductor of any shape, and here we want to calculate the value of electric field. Now we'll take a Gaussian surface. We take a Gaussian surface in the form of a pillbox, and the area of the pillbox is ds. Area of the pillbox is ds, and surface charge density is sigma. Now the electric field is directed, of course, parallel to the outward normal of this cross-sectional area. This is the direction of electric field. Because it is a conductor, if the electric field has a, of course, direction like that, this is a component and this is another component. लेकिन अगर ये component कंडक्टर के along है तो कंडक्टर के अंदर ये इलेक्ट्रिक फील्ड इलेक्ट्रॉन को इधर की तरफ मूव कराएगा, but the electron should not move because there is no potential difference between any 2 points of the conductor. So this component of the electric field is zero. So the electric field has only this normal component which is normal to the cross-sectional area, and that is why when we calculate Gauss's theorem, it is E dot ds is equal to q by epsilon naught. So from Gauss's theorem, E and ds, we will get only the flux at this point and the curved surface, the outward normal on the curved surface, and the electric field, of course they are perpendicular to each other. So on the curved surface the value of electric flux is 0. So the only electric flux is E into S on the cross section, and this is q by epsilon naught. So this is E into S is sigma into S by epsilon naught. S is cancelled, so the value of electric field is sigma by epsilon naught. So if this is a conductor of any shape, here the electric field will be outward normal and the value of electric field is sigma by epsilon naught. So this is the electric field near a कंडक्टर ऑफ एनी शेप. किसी भी शेप के कंडक्टर पर आप इलेक्ट्रिक फील्ड को कैलकुलेट कर सकते हैं. नाउ वी कैन कैलकुलेट द फोर्स exerted by charged particle on those charged particles which are of course residing on the same conductor. Suppose this is a conductor of any shape. We want to calculate the force exerted by, of course, this portion of the conductor due to all the remaining portion. Suppose this is completely charged. It is completely charged. Now we will cut that is this portion. This portion is taken out and consider this portion and of course this portion separately. We will calculate the value of electric field at a point very close to the conductor, very close. One point P1 inside and P2, it is also very close, but P2 is P1 is inside and of course P2 is outside. This is P1 inside and P2 is outside. This portion has electric field, this portion has electric field E1, electric field due to this portion, and the remaining portion will also have electric field only towards the right direction, and the electric field is due to the small portion, and E2 is the electric field, E2 is the electric field due to this remaining portion S2. E2 is the electric field due to remaining portion E2. At outside point both are directed in the same direction. Outside point both are directed in the same direction. Field due to this portion and field due to remaining portion both are directed in the same direction. Hence E1 plus E2 is equal to sigma by epsilon naught. Now for point P1, the field due to a smaller portion is towards right and field due to remaining is towards left. So now at point P1 inside, field due to a smaller portion is towards left, and due to bigger portion bigger portion it is towards right. तो छोटे वाले पोर्शन की वजह से लेफ्ट में होगा और ये जो बड़ा वाला पोर्शन है उसके वजह से इलेक्ट्रिक फील्ड ऑफ कोर्स बाहर की तरफ होगा. दोनों एक दूसरे को अपोज कर रहे हैं. The field due to a smaller portion and the remaining portion opposes each other. So E at P1 is E1 minus E2, and we know that inside the conductor the value of electric field is 0. Inside the conductor the value of electric field is 0, so E1 is equal to E2. Now E1 plus E2 is sigma by epsilon naught. Hence E1 plus E1 is equal to sigma by epsilon naught. So 2E1 is equal to 2E2 is equal to sigma by epsilon naught. Hence E1 is equal to E2 is equal to sigma by 2 epsilon naught. So we can say that if here we are considering at this portion the electric field due to remaining portion is sigma by 2 epsilon naught, and charge at this portion is sigma into S. So force on this smaller portion, force on the a smaller portion due to charge on the bigger portion. Charge on the bigger portion is E into Q, is sigma by 2 epsilon naught, and this is sigma into S. So the force is half sigma square by epsilon naught multiplied by S, and the force per unit area is half sigma square by epsilon naught. So if we charge a body and consider any small portion of the conductor, the small portion of the conductor experiences a force due to remaining portion, and that remaining portion has a tendency to push this small portion away, and this is not true with this. इसी के साथ ये सही नहीं है, किसी दूसरे पोर्शन को भी देखेंगे तो उस पोर्शन पे भी रिमेनिंग पोर्शन की वजह से बाहर की तरफ आउटवर्ड प्रेशर लगता है, फोर्स लगता है, एंड फोर्स पर यूनिट एरिया प्रेशर, एंड दैट प्रेशर इज, और वो जो प्रेशर है आपका, इसको हमने कहा P इज इक्वल टू हाफ सिग्मा स्क्वायर बाई एप्सिलॉन नॉट. दिस इज हाफ सिग्मा स्क्वायर बाई एप्सिलॉन नॉट. अब इसको हम लोग फिजिकली देख सकते हैं. फिजिकली इस तरीके से देख सकते हैं कि सपोज मान लीजिए कि यहाँ पे मैंने एक सोप बबल क्रिएट किया, एक सोप बबल हमने यहाँ क्रिएट किया. इस सोप बबल का एक अपना रेडियस है. दिस सोप बबल हैज अ रेडियस. नाउ ये आपका कंडक्टिंग है. नाउ एक एबोनाइट रॉड को मैंने चार्ज किया एनी हाउ किसी तरीके से, एंड फिर मैंने इसको टच करके इस बबल को चार्ज कर देते हैं. हम देखते हैं कि जैसे ही आपका बबल चार्ज हो जाता है, चार्ज होने के बाद द साइज ऑफ द बबल और इवन द ड्रॉप ग्रोज. ये साइज जो है किसी भी चार्ज ऑफ कोर्स बबल या ड्रॉप का साइज चार्ज करने के बाद वो बढ़ जाता है. उसका रीज़न ये है कि सपोज आप किसी चार्ज बबल या ड्रॉप को देखेंगे तो हम लोग क्लास 11 में सरफेस टेंशन में पढ़ते हैं कि ड्यू टू phenomenon of surface tension, the liquid drop or bubble has a tendency to minimize their surface area. Due to phenomenon of surface tension, a liquid drop or a bubble has a tendency to minimize their surface area. वो अपने surface area को minimize करना चाहते हैं. और अगर वान डर वाल्स फोर्सेस का एक रिपल्सिव पार्ट भी होता है, व्हेन द डिस्टेंस बिटवीन टू मॉलिक्यूल इज वेरी वेरी स्मॉल, द मॉलिक्यूल स्टार्ट रिपेलिंग ईच अदर. In the similar fashion, as if the distance between two nucleons in a nucleus is very very small, less than 1 Fermi, the nucleons start repelling each other. तो ठीक उसी तरीके से अगर ये आपका ड्रॉप है तो ये ड्रॉप सरफेस टेंशन की वजह से कॉन्ट्रैक्ट करना चाहता है. इट वांट्स टू मिनिमाइज इट्स सरफेस एरिया, एंड व्हेन इट स्टार्ट कॉन्ट्रैक्टिंग at a particular situation, when the distance between two molecules is very, very small, the molecules start repelling each other. And there is a excess pressure acting in the outward direction, and this excess pressure P is equal to 2T by R for a drop, one surface, and P is equal to 4T by R bubble for two surface. So the drop is in equilibrium because the excess outward pressure, there is excess pressure inside the drop or bubble acting towards away, and of course due to surface tension 2T or 4T by R is acting in the inward direction, which is try to minimize the surface area, and the two are equal to each other. And at the equilibrium, if the drop P is 2T by R, if it is a bubble, it is 4T by R. Now if we give some charge, there is an outward pressure P on the drop, and now this is held by this excess pressure is held by this outward pressure, and the equation is half sigma square by epsilon naught plus 4T by R. In the case of bubble, it is of course this is 4T by R, and this is excess pressure. Initially the excess pressure is 4T by R. Now excess pressure plus half sigma square by epsilon naught is equal to 4T by R. So due to this, the minimizing tendency of the surface, the contracting tendency of the drop or bubble decreases, and the bubble start of course expanding. If we want that this excess pressure should be 0, then half sigma square by epsilon naught will be 4T by R. If half sigma square by epsilon naught 4T by R, then the excess pressure inside the bubble or drop will be 0. Excess pressure will be 0, and excess pressure will be 0 for sigma is 8T epsilon naught R root under, and the charge given is sigma multiplied by 4 pi R square. And if you want to calculate the potential difference, C is equal to Q by V. So V is equal to Q by C. Q is sigma multiplied by 4 pi R square, sigma is given, and of course C is 4 pi epsilon naught into R. So potential difference or potential of the drop for excess pressure to be 0, potential of the drop for the excess pressure to be 0 is 4T epsilon naught by R multiplied by 4 pi R square and divided by of course 4 pi epsilon naught R. So we have discussed that if somebody is charged, it is drop or bubble, the charged body has a tendency to expand, and hence अगर ये क्वेश्चन आपसे पूछा जाए कि अगर किसी बबल या ड्रॉप को आप चार्ज कर देते हैं तो क्या होगा, तो उसका साइज बढ़ जाएगा और